Okay, here we go. All right, so we need to make sure that we are clear on our vocabulary. And I think we talked about this yesterday, but a function is that relationship that maps inputs onto outputs, right? And the important thing is each input is matched to exactly one output, okay? Please don't ever define, now that we're bigger kids, don't ever define a function as something that passes the vertical line test. In the Cartesian coordinate plane, the XY coordinate plane, yes, the vertical line test is a real thing. But in the polar coordinate plane, which this course is a lot, we spend a lot of time with that, no, they're circular, so they don't pass the vertical line test, but they are still functions. So we're kind of throwing that definition out and we're going with the real definition, which is what's written here. All right, so functions are input-output machines. You put numbers in and you get numbers out. The inputs are called the domain. The outputs are called the range. Now, the input variable, which again, in the Cartesian coordinate plane, we can talk about x. That doesn't work in other coordinate systems. So we have another word to define them. Instead of saying they're the x coordinates, we say they are the independent variable. The inputs, the domain, are the independent variable, and the outputs of the range are the dependent variable. Can somebody explain that? We talked about this yesterday. Can somebody explain to me why one is independent and the other one's dependent? Can you think of a reason why that would be? Think of when you were a little kid and you were just learning about functions. So you had something like f of x equals x plus 2, and your teacher told you this was the same as y. Remember that? It is, that's fine. And then the teacher said, okay, let's draw a picture of this. So she had you set up a T-chart, right? And what's the first thing you did when you had to graph this using the T-chart? You made some x's, right? So I don't know what you used, but you picked some x's. And then you used these x's to figure out your y's. You see why that's called dependent? That value depends on this one. Where did these come from? You just made them up, right? They're totally independent of everything. You just make them up. But these are the dependent variables. Okay, take a minute, example 1, and sketch these two. Would you sketch these for me? See if you can figure out. One is given to you in written form, and one is given to you in tabular form, in a table. So see if you can draw a picture of that. Doesn't tell you to do this, but for that first one, for A, could you think of an equation that described that? It doesn't tell you you have to do that, but could you?
Just y equals x plus 1.
Y equals
X plus 1.
X plus 1?
1/2.
1/2 x plus 1? Because it halves the input and then adds 1? Okay, so what shape is that? I know we're going to graph it here in a minute, but when we graph it, what shape are we going to get? Isn't that a line? mx plus b. So I saw some of you building a table of values and plotting individual points, and that's perfectly okay. But I know this is going to be a line. I know the first point I'm plotting is put in -4. So when I put in -4, I got -1. And then the last point I'm plotting is when I put in 4, and I got 3. So could I just plot those two and connect them with a line, since I know it's a line already? You don't have to do that. You can plot individual points. That's perfectly okay. But another strategy is to recognize you're dealing with a linear relationship here. B, I don't believe is linear. What does B look like? Plot them. Did you get just a set of, like, I don't know, I don't even know what shape that would be, I don't know. We did this yesterday in the other class and somebody said it's a dinosaur. I don't see it myself, but it's just some points. You got them plotted? You okay with that? Okay, down at the bottom, these are very, very important notes, but they're pretty basic and easy, at least part of it. What do you think we mean by an increasing function? Look at the picture. It goes up. Basically, left to right, your pencil is going up. Mathematically, we say, as the inputs increase, so do the outputs, right? Now, what does decreasing mean? Decreasing means that your pencil goes down. You got a pass or something?
Mrs. Lewis is sending me an email.
So decreasing means as the inputs increase, the outputs decrease. So left to right, your curve is going down. Now, the next part is something you may not be as familiar with. Concave up. Concave up is like a cup. It will hold water. Okay, that's concave up. If a curve is concave up, it means that the rate of change is increasing. And folks, what's another word for rate of change? Slope. So if you have a concave up shape, that means for that function, the slope is increasing at those points. Concave down is just the opposite. Concave down means that the slope is decreasing, okay? All right, so example 2 on the back. Take a minute with your partner and see if you can figure out, using that random shape, see if you can figure out where the curve is doing what it says. Find the curve. Go back and look at Jerry's. Remember that your answer must be written in interval notation, so you're using parentheses and brackets. Notice in the directions it says find the open intervals. So you're only going to be using parentheses. The directions say open intervals. All right, see what you can figure out.
Would it be -2? Then, so increasing, would that be like 4 to 7? But it does matter. Yeah. Then for this to be able to put like this and this. So it would be like -2, 0, and right? Yeah, because that's concave down. increasing and concave down. This is concave down, but it's decreasing. Yeah, but it's, no, sorry, I was talking about right here, but whatever. This is concave down, but it's also increasing, so that means I'd be able to put here too. Decreasing. Right, that's what you'd say. We write it just there. We could do that and then we also do like 47.
This whole H.
Alright, we could try that.
I've never had it.
So then for decreasing, yeah, that's true. Increasing is just in general, when it's kind of like the slope is up, that's what we put when it's so like that would be increasing and downwards in that way. With that when we put increasing, it's
All right, let's see what you've come up with. Where did you say this curve was increasing? Increasing. Where did you say? Now remember, your intervals are your x's. So what to what? Where did you say we were increasing?
4 to 7.
4 to 7. I would agree with that. Doesn't look like we're going up from 4 to 7. Are we going up anywhere else?
Negative 2 to 0.
Who put negative 2 to 0?
Remember, increasing means going up.
-2 to 0.
So I believe negative 2 to 0. Aren't they going up on this part? Now after that, what happens? Going down. Here I am going up. Very good. Everybody okay with that? Now where am I going down?
-4 to -2.
Negative 4 to negative 2. And
0 to 4.
0 to 4. Right? 0 to 4. Right, any question about that? All right, where does the picture appear to be concave up? Now remember, concave up means it's like a cup. It's going to hold water. So what do you think? Where do we appear to be concave up?
2 to 7.
From 2 to 7? Would everybody agree with that? Because this little piece right here is actually concave down. Okay, so starting here, 2 to 7. All right, increasing and concave down. So were you able to find any part of the curve that was both increasing and concave down? Now I kind of helped you out because in blue, I have the increasing pieces. So it's got to be a blue piece. Are any of those blue pieces also concave down?
-2 to 0.
Negative 2 to 0. And then decreasing would be my black pieces. Are any of those concave up?
2 to 4.
2 to 4. Anybody have an issue with that? Okay, now we're gonna do something really fun. Look, no, you thought that was fun. This is gonna be really fun. Look at that last problem. It's the opposite. They have given you intervals and told you how the curve behaves, and now you are gonna graph the curve. Now, there are lots of answers, lots of possible answers, okay? But you wanna get a shape, some shape on your paper that matches all of the criteria, okay? Go, and then we're gonna put them on the board and look at 'em.
Yes, so negative 4, it's increasing. Okay, it's negative 4. It's increasing. And concave down.
We don't know how far it's going.
Ooh, okay, hold on. This is second. So we're looking at negative 4. It's gotta go up, but it's also concave down. Look how hot it goes. Check. 2 and 5 and 7. You can't go that far. It's 5 and 7. Back to your one that's
Sometimes, you guys are really smart, you'll do whatever you want, but sometimes when I do problems like this, I like to lay out my domain, which from the intervals there are from -4 to 7, and then just kind of make a list of what I know. So at this point, I'm increasing and concave down. That helps me to kind of just organize it, but you don't have to do that. If you're struggling, maybe try that. Maybe you've already got a picture. I would like to see some of these pictures after you get them done. Let's look at some of these. Wait, you got one? Put it up here. Put it right here. Let's see what others think. Patrick, you got one too? You got a picture? Put it right here. It'll be all right?
Yeah.
Okay, put it right here. Let's get one more. Patrick's not gonna use there. Let's get one more. Does anybody else have one you'd like to share? What are you smiling about, Jacob?
Jacob, yours is definitely good.
Don't think it's right.
Pop it up, let's take a
He's a
look at
good
it.
artist.
Go ahead. Worst that can happen is you don't have to seal it.
Not quite.
Something like that.
Something like
Do I have
this.
to draw a graph? Like, just not
No, you don't have to. You just draw a shape. Oh, actually, we do need to have some kind of labels on here. We need to know, like, where, like, maybe an x-axis at least. And we really have no labels on our y-axis, right? We have no idea how high or low this thing goes, but we should have our x's labeled so that we can check to see if we're doing the right thing in the right intervals. while we're waiting for these guys to finish, what does it mean in my picture, when I've got something like this? At this point, it's said I'm concave up and concave down. What's happening at that point? It's going from, so it's concave up, and then it becomes concave down. So isn't that like that point right there? And what's happening when it's both increasing and decreasing? What's happening at that overlap? It goes from going down to going up, so maybe it's like here. So this, like, I don't know, vertex point or whatever you want to call it, that is, actually that has a name. It's what's called a critical value, a maximum or a minimum. And that happens when you go from increasing to decreasing or vice versa. Okay, so let's look at this. So when, this is awesome, thank you volunteers for doing this, because this is kind of tricky. So Quinn, you said -4 is increasing and concave down all the way to 0. And then it changes to decreasing. Yeah, I'm not sure what that little guy is there, but that's okay. And then like that maybe, huh? So at 0, it turns around. Or no, at 1 it turns around. So you were right, I'm sorry. You're right, yeah, at 1. It's going up. There's 1 right there. And then it starts coming back down. Okay, that's good. And that was at 1. And now it's concave down and decreasing. And then what happens at 3? The concavity changes. So here's your 3 right here. So coming into that, we are concave down. And then we have to change to concave up. That looks okay. That looks good, okay. And then we're decreasing and concave up until we get to 5. And then, yeah, I think let's move this point over to here. Would that be better? Because that's where we're changing from increasing, or no, at 5, increasing and decreasing changes, and we're concave up, okay? And then we're increasing to 6. Okay, wait, that interval, that whole interval is increasing. So, I think that part's wrong. Anybody have a thought? What's happening there between 5 and 7? It starts increasing, that's right, but the concavity changes at 6. So it goes from being concave up to being concave down. So can you envision that? So here's your concave up, and then at 6, we become concave down. So we have a little squiggle like that. Does that make sense to you? Okay. Anybody have a question about that? Does that picture make sense to you? All right, let's check one more. Let's look at, is this yours, Patrick? Okay, let's check yours. Is he right? From -4 to 1, we are increasing and concave down. That looks perfect. And then at 1, we start decreasing. We're still concave down until we get to 3. And then, see how he switches right here from being concave down to being concave up? Good. And then, what was that? That was 3. So then we're decreasing and concave up. And at 5, we started increasing, okay. Well, I guess you're okay, because we don't know what's happening out here, right? But yeah, okay, that's all right, concave down. That's all right. Perfect. Very, very good. All Alright, you okay with that? You're gonna get to do a couple of those in your homework. You okay? Alright, let's look at this, extra sheet here. Can we predict maximum heart rate? Would you do the front side of that, see what you can come up with? It's really easy, you should have no problem with it. Work on it together for a second, and then I'm gonna give you, a few extra notes. Let's do the heart rate problem.
Because you're adding 5. Oh wait, but it's 35, so you would want
Went up 15, and then down to 2. Yeah, sure.
It's one so you track it. Right.
That's what I was trying to say.
The maximum heart rate is
No, they too easy for me.
160.
So,
Oh, okay, I know what it is.
Jacob, your picture was fine, except at 7, you started decreasing too fast. It's still increasing at 7, but it's fine. Other than that, I think you did. Yeah.
I think it's negative.
No, it doesn't have to be full. I mean, that is a concave down shape. You don't have to say negative 1. This shape
I
is
think it's negative X because the y-axis
It has to be, yes, it has to be increasing.
x-axis goes by increments of 10.
That means every time you increase it,
So
it's
it has
negative.
But that's why.
Because 20 is 200 and if
After
you put 20 up here, we have 20 plus
I know, but
220.
Yeah,
60.
when the line enters,
and they wouldn't necessarily have to, because it's 60.
that's what this
It's
is.
concave down thing that we don't know what it
there
is.
were reasonable values of
So it's just, and it's just negative X. It's actually decreasing.
Plus 220. Yeah, because that's the y-axis of the, or y-intercept of the. Anywhere from like 0 to 100 because those are like average ages.
Okay, so what are reasonable values for age? Yeah, some people live more than 100, but I would say probably not more than 105 or something. I don't know, I don't know who the longest living person is, but it would be something like that. So basically, what you're asking is what's the maintenance problem? What are the acceptable X values? Yeah, probably in an interval instead of an interval, but yeah. And you could, yeah. All right, so let's talk about these guys, we have one more thing to do. What did you say, I think 1A wants words. 1A says, what's the relationship between age and maximum heart rate? Exactly. So this is gonna be a decreasing function, right? As the inputs go up, the output's gonna go down. Very good. Predict the maximum heart rate of a 35-year-old. How did you do that? Because it's not in the chart. First of all, what are some answers you came up with for a 35-year-old? Everybody says 185. Everybody matches. How did you do that?
220 minus their age.
What?
220 minus their age.
220 minus their age. Did they tell us that?
No, I just know it from anatomy.
You knew it from anatomy. Okay. What can you tell from what's given? That's awesome, by the way. What can you tell from the given now? Take a look at, Josie, what'd you discover? Or what'd you notice?
The max heart rate goes down by 1 for every year.
It looks like if you look at the chart, if you go down, look, you went from 14 to 18 in age, and your heart rate went down 4. And then in the next one, you went, in age, you went up 7, and your heart rate came down 7. So doesn't it look like it's pretty much a 1-to-1? All right. So the graph shows the relationship, okay. What is the maximum heart rate of a 60-year-old? Well, you can get from your chart, you could use Julia's formula, or you could just look at the chart. So if we're 60 years old, our heart rate's gonna be 160. And what if the heart rate's 200? That's a Y value, right? So if Y is 200, it looks like X is 20 years old. All right, so the equation you come up with, write an equation that can be used to determine the maximum heart rate of someone who is X years old. That would be Julia's equation. But even if I didn't take anatomy, which I didn't because I can't cut all that stuff up, it grosses me out. But even if I didn't take anatomy, I can tell from whatever you discovered. Didn't you say the slope was -1? And the y-intercept is, according to your picture, 220? So -1x plus 220? So that's exactly right. That's exactly right. Okay. What do you think is reasonable values for x? Patrick and I were discussing that earlier. What did you come up with? X is your domain. What did you come up with for reasonable values? Gotta be bigger than 0, because you're never negative, right? Bigger than 0. And then probably, he originally said 100, and I said, well, some people do live to be more than 100. So he and I agreed on maybe 105. But you could have, there might be somebody 107, 108, I really don't know. But somewhere up in that vicinity would be your max. Do you think it's possible to have a maximum heart rate of 100 beats per minute? Ellen, why not? You're shaking your head no. Why not?
Because people don't live to 120 years old.
So, yeah, in order to use our equation and get 100, you'd have to be 120 years old, right? And I don't think that happened. I don't know. Maybe, I've never heard of someone living that long. I certainly don't think it's reasonable to think that. Okay, well, the formula, blah, 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 they got another one for women. So using the woman formula, find the heart rate for somebody who's 32 years old. So, did you do it? What'd you come up with? Use a calculator. What'd you come up with? You just sit down, stare at me. Plug in 32 into the woman formula.
178.
What is it, about 178 beats a minute? Okay, Miss Anatomy Queen, why does the formula work for men and not for women? What's that about?
Created for men. Men created the formula, they created it for men.
Why is there a difference though?
Women's hearts are different, women's bodies are different.
Yeah, okay, all right. Maybe we'll ask Mrs. Mills. Okay, backside, real quick, backside. I want fill in these quick notes. We've already talked about this, but I just wanna make sure that we have this definition down. A function describes the relationship between what? An independent variable and a dependent variable. That's what a function does. It shows the relationship. You might add to that, just for your own remembering, each input, which is your independent variable, right? Each input is mapped or paired with exactly one output. That's what makes a function. When you are told to evaluate a function, you will see that a lot in the directions, evaluate the function. You just did it with the women heartbeat. To evaluate a function, what do? You determine or find the output value for the given input value, right? And that can be done with an equation, like Julia's equation. It can be done with a graph. It can be done with a table. We already talked, what are the set of inputs called? The domain. And it's important to know that your domain variables must be defined in the problem. So if you had a function like this one, which we'll run into, we haven't yet, but if you had a function like this, you would have to restrict your domain, right? And say, okay, my domain cannot include 5. So when we talk about the inputs, they have to be defined. Yep, they have to be defined values. All right, set of outputs is the range, and then the notation there. Our functions can be named F, G, A, B, P, Q, whatever you want to name them. That letter F of, H of, P of, that's the name of the function. And then you have your input and output variables. Okay, last thing today. I need everybody to do problem number 1 and 2. Check your understanding. I need you to do this problem. We're gonna get them on the board, make sure we all match, and then we'll be done for the day. Lunch, okay, awesome. Cherry tomatoes and candy kisses, my 2 favorite foods. And these are just a bunch of cherry tomatoes. They're kind of, I don't know, they're not like cherry tomatoes, but they're like cherry tomatoes. Thank you, sweetheart. Are you going back down there?
Yeah.
Tell her thank you. Tell her she made my day.
I will.
You know, I taught the nurse back in 83 or 84, somewhere in that vicinity. Alright, let's talk about this first one and make sure we're all on, the same page here. Question number 1 says, what is the independent variable and what's the dependent variable? What did you say? Independent was radius and dependent is volume. Does that make perfectly good sense to everybody? If in fact you were confused, you could look at the chart they set up for you, because when you say R and V of R, that's your independent variable, and V of R is going to be your dependent variable. Perfect. All right, I completed the chart. I don't know if I got the right numbers or not. These would be the exact values right here. So I started with those. A later question asked me to do some comparing, so I went ahead and got decimals. It's always best to leave your answers exact. So even though these may not look very nice to you, these are the best answers. But for comparison purposes later, I like to have my decimals here. All right, be okay with that? C. Describe how increasing the radius affects the volume. Makes the volume bigger. But let's go a little more in depth. Is it like our heartbeat problem, where every year of age took away 1 beat of the heart? No. Here, the volume is increasing much faster than the radius. Would you agree? Why is that?
Because R is
Because it's
cubed.
being cubed. Exactly, it's being cubed. And you know what x equals y cubed looks like? This is what a cubing function looks like. So as x goes along, y is going up, right? So be clear in that explanation. Yes, the volume is increasing, but at a much greater rate because the function is cubed. All right, what's a reasonable domain and range for this problem? Thoughts? What? 1 to 10? For R?
Yeah.
Okay, let's talk about that. What are we talking about here? We're talking about the volume of a sphere? So are there spheres who could reasonably have radii or have a radius bigger than 10? Yeah. Are there spheres that could have a radius less than 1? Yes. So let's see. What is the smallest a reasonable sphere radius could be? 0, right? 0. So for domain, clearly 0, we can't go smaller than 0. Now how big can a sphere be? Pretty big, right? Think of the Earth. I know it's not perfectly a sphere, but for purposes of volume and stuff, they think of it as a sphere. And aren't there things bigger than the Earth? Like, isn't Jupiter bigger than the Earth? So really, a reasonable domain for this formula would be anything positive. And of course, if we're gonna let the radius get ginormous huge, then what's gonna happen to the volume? It's gonna get even bigger ginormous, right? So in this case, your reasonable domain, we're talking about a sphere, your reasonable domain and range are just positive. Okay, finally, the last one. Clearly define your variables. Now, I just put x and f of x. You might have put something else. Don't put x and y, or p and q. It's gonna be p and f of p. All right, so how did you define your variables? What did x stand for? Or whatever letter you used.
How many feet the skid mark was?
So the length of the skid mark, so feet, well, let's just say length of skid mark. Okay, perfect. And then what did f of x stand for? Josie?
The speed of the car when it hit the brakes.
Just real quick to make sure. Yep. So what function did you come up with? This was an easy one, cause they told you. What did they say? Don't let the words confuse you. What was your function rule? F of x equals
Square root of 21x.
square root of 21x. Like that? Perfect. Alright, you've already got your homework. You've got 4 minutes. I don't care if you want to start it now. If you have something else to do, you can go ahead and get your phones. That homework will be due on